Hi. In this video, we are going to continue with our number theory course, and today we are going to talk about a very important topic. It's quadratic reciprocity. So this is a very great idea, and we start off by with something that we have already seen before, which is squares modulo a prime. We have made a video earlier in this course about squares modulo a prime. So you should check that video out. I'm just going to quickly tell you what context we are going to use. So we are saying let P be an odd prime. Let P be an odd prime. We say that we say that an integer A, which is not a multiple of P, not a multiple of P, is a quadratic residue mod P if the equation x square is congruent to A mod P as an integer solution. As an integer solution. So we have talked about quadratic residues earlier. If x square is equal to A mod P has an integer solution, then A is a quadratic residue, right? If the equation doesn't have a solution, doesn't have an integer solution, then A is a quadratic non-residue. A is a quadratic non-residue. So please go back to the previous videos and revise this idea of quadratic residues and non-residues. Uh, we will be using that extensively to explain the law of quadratic reciprocity here, right? So also another idea here is if A and B are two integers, that are congruent to each other modulo P, that are congruent to each other modulo P, and if one of them is a quadratic residue mod P, and if one of them is a quadratic residue mod P, then so is the other. Obviously, if the two integers are congruent to each other, then if one of them is a quadratic residue, then we can say that the other one will also be a quadratic residue. So this is the idea of and the definition of quadratic residues. Now we start off by saying how many quadratic residues will be there for P being an odd prime. So if P is an odd prime, then there are exactly P minus 1 by 2 quadratic residues. There are exactly P minus 1 by 2 quadratic residues that are non-congruent modulo P, that are non-congruent modulo P. So what is the meaning of that? Let's look at it with an example. Let's say P is 5. This is an odd prime. Let's take the all the numbers 0, 1, 2, 3, and 4 and let's square them. So we are getting 0 here. All of the calculations are being done mod 5. We are getting 1 mod 5 here. We are getting 4 mod 5 here. We are getting 9, which is also 4 mod 5. And again, we are getting 1 mod 5, right? So notice that when you do x square is congruent to A mod P, right? And here it is x square is congruent to a mod 5, right? So which a's will have integer solution? You should realize that only a's possible are 0, 1, and 4. So 0, 1, and 4 are quadratic residues mod 5, right? What is not possible? 2 or 3 are basically not possible. What do I mean by that? Basically, the equation x square is congruent to 2 mod 5 doesn't have a solution. Similarly, x square is congruent to 3 mod 5 also doesn't have a solution. So 2 and 3 are quadratic non-residues, whereas 0, 1, and 4 are quadratic residues mod 5, right? And now we can say that there are 3 quadratic residues mod 5 that are non-congruent, right? And that is what is happening here. So we will exclude the case 0 because 0 a is 0, then 0 is a multiple of 5, right? 0 is a multiple of 5. So we'll exclude this case and we'll say 1 and 4 are the two quadratic residues for this. So it also fits the formula p minus 1 by 2 because 5 minus 1 by 2 is basically 2. So that is what I wanted to explain. Now let's look at another example and try to establish some pattern. So let's take the example of p is equal to 7 and p minus 1 by 2 is equal to 3, right? Now here, what are the quadratic residues mod 7? So let's calculate 1 square, 2 square, 3 square, 4 square, 6 square, right? So this will become basically 1, 4, 2, and this will become again 16, which is basically 2, and this is again 4, and this is again 1. So we have 1, 2, and 4 are quadratic residues mod 7, right? And what are the non-residues? 3, 5, and 6 are quadratic non-residues. Non-residues mod 7, right? Now let's try another thing here. Let's try to find out a power 3 is congruent to x mod p. So what are the values of a cube? What is a cube congruent to, right? So if you take a cube, 1 cube, 2 cube, and 4 cube, let's find out what is it mod p. So 1 cube is 1 mod p, 2 cube is also 1 cube is basically 1 mod 7, 2 cube is also 1 mod 7, and you will realize that 4 cube 64 is also 1 mod 7, right? On the other hand, when you do 3 cube, 5 cube, and 6 cube, what are we getting? 3 cube is 27 and 27 is minus 1 mod 7. 5 cube is 125 and 125 is basically again minus 1 mod 7. And 6 cube is 216 and this is also minus 1 mod 7. So you should notice a special thing happening here. What we are getting is that all the quadratic residues, when you cube them here, when you're doing mod 7, 1, 2, and 4 were the quadratic residues. When you do a cube, it is coming as 1 mod 7 in all three cases for the quadratic residues. And it is coming minus 1 mod 7 in the cases when they were not quadratic residues, right? 3 cube, 5 cube, 6 cube, it's also coming minus 1 mod 7. And what is the significance of doing a cube? Why did we do a cube? So we know that 3 is equal to p minus 1 by 2 in this case. So what we are actually calculating is a power p minus 1 by 2 mod p, right? And we have gotten that a power p minus 1 by 2 mod p is 1 mod p if a is a quadratic residue And a power p minus 1 by 2 mod p is congruent to minus 1 mod p if a is a quadratic non-residue, right? So I'll just write down the conclusions from this experiment. We are getting a power p minus 1 by 2 mod p is congruent to 1 mod p if a is a quadratic residue mod p, right? And similarly, a power p minus 1 by 2 mod p is congruent to minus 1 mod p if a is a quadratic non-residue. Let's take another example and try to set it on a firmer footing. This is my conjecture right now. This is a statement that we are hoping is true, right? So let's take p as 11. That's the next prime number, 11, odd prime number, right? So p minus 1 by 2 is what? It is 5, correct? Let's find the quadratic residues for p. P is equal to 11. So we have 1 square is 1. Then we have 2 square is 4. 3 square is 9. 4 square will be 5. All of it is mod 11, by the way. 5 square will be 3. Then 6 square will be also 3 because 6 is minus 5 mod 11, right? So we get 6 square is also 36. Yeah, correct. And 7 square will be basically 49, and this is 5. Notice that now everything will repeat. After 5, everything will repeat after this because 8 square will be congruent to minus 3 square, which will be congruent to 9. So you'll get the same values here now, right? So basically we have found out that 1, 4, 9, 5 and 3 are quadratic residues mod 11, right? And what are the non-residues? 2, 1, 2, 3, 4, 5, 6, 7, 8. 2, 6, 7, 8 and 10 are quadratic non-residues, right? Mod 11. So now what I want to check is whether this rule is valid or not. This thing that we tested out for p is equal to 7 earlier, right? So what I want to see is a power p minus 1 by 2, a power, in this case it is a power 5 mod of 11, right? And let's find out the values for the set of numbers here and the set of numbers here, right? So if you try, so clearly 1 power 5 mod 11 is congruent to 1 mod 11. Let's try 3 power 5. 3 power 5 is actually 243, and mod 11, 243 mod 11 is actually 220 and 22 and 1. Yeah. So 3 power 5 mod 11 is also congruent to 1 mod 11, right? Similarly, you can test others also. 4 power 5 would be 256 times 4. So that will be 1024. And if you think about it, 1024 will be 990 and then 34. That is also 1 mod 11. So we are getting that all of these numbers are giving, when you do a power 5 mod 11, they are congruent to 1 mod 11. And let's check out the numbers in this set now. So 2 power 5, 2 power 5 is 32, and that is clearly minus 1 mod 11. Now 6 power 5, 6 power 5 would be basically minus 5 power 5. So that will be minus 3125, right? Mod 11. Or you can just calculate it directly. 216 times 36. So 216 itself is 216 is minus 4 mod 11, and 36 is plus 3 mod 11, right? So this is minus 12, which is minus 1 mod 11. So you can confirm it yourself. I'm just doing a rough calculation and I'm getting all of these numbers in this set, which is the set of quadratic non-residues, will give -1 mod 11, right? So it seems that the criteria is coming true here, right? This is working, this result. So basically what we have figured out is a way to determine, a way to determine whether or not, whether or not a given integer, let's say a, is a quadratic residue mod p, is a quadratic residue mod p. And this is known as Euler's criterion. This was first found by Euler's, and Euler's criteria is stating that if p is an odd prime, if p is an odd prime, and a is an integer relatively prime to p, and a is an integer such that GCD of a and p is equal to 1, then a power p minus 1 by 2 is congruent to 1 mod p if and only if a is a quadratic residue mod p. And a power p minus 1 by 2 is congruent to -1 mod p if and only if a is a quadratic non-residue mod p. So this is what we have got so far, Euler's criteria. The theorem says that if a and p are co-prime and p is an odd prime, then a power p minus 1 by 2 mod p is a quantity that is either 1 or -1, depending on whether a is or is not a quadratic residue mod p, right? So now, using Euler's criteria, we can define, or another mathematician, Legendre, defined a symbol. So it's called the Legendre symbol, and this is what it is called. So if P is an odd prime, in order to facilitate calculations, we will be using this Legendre symbol. And if P is an odd prime and A is an integer relatively prime to P, relatively prime to P, then the Legendre symbol is denoted by A by P in brackets, and it is defined to be, is defined to be 1 if A is a quadratic residue, A is a quadratic residue mod P, and the symbol, Legendre symbol, is equal to -1 if A is a non-residue, quadratic non-residue mod P. Right? And now we will apply Euler's criteria to this. So we will be able to say that the Legendre symbol should be equal to a power p minus 1 by 2 mod p is equal to basically a over p mod p, right? Because Euler's criteria is saying that this is 1 if it's a quadratic residue, and we have defined the Legendre symbol to be 1 if it is a quadratic residue. So obviously this should be same as this, right? Similarly, it is -1 if it is a quadratic non-residue according to Euler's criteria. And again, the symbol is defined to be -1 if it is a non-residue. So we'll be using that in the future. But before that, let's get a little familiar with the symbol, Legendre symbol, and let's find out some basic values. So let's try to find out whether 2 by, what is the value of this, right? According to the symbol, what is the meaning? This is 1 and -1. These are the two possible values of this. And that depends on whether A2 is a quadratic residue mod 11 or not. Depends on whether 2 is a quadratic residue mod 11, right? So what is the meaning of that? Is there a solution to the equation x square is congruent to 2 mod 11? If there is a solution to this equation, 2 is a quadratic residue mod 11, right? So if you take all of the squares from 1 square till 10 square, right? In order to find out the quadratic residues mod 11. So this is 1, this is 4, this is 9, this is 5, and this is 3, right? And after that, it keeps repeating. This is 3, this is 5, this is 9, right? And this is 4, and this is 1. So we know that the quadratic residues are 1, 4, 9, 5, 3. So 2 is not a quadratic residue, it's a non-residue, so this should be -1, right? The Legendre symbol 2 by 11 should be -1. Similarly, the Legendre symbol 5 by 11 should be +1, because we can see clearly that 5 is a quadratic residue mod 11, right? From here, it should also be obvious that 1 over p, if you do a Legendre symbol of this, that is equal to 1 for all p. Why? Because 1 is always a quadratic residue mod p, because you can always say 1 square is congruent to 1 mod p, right? Correct. So 1 over p, this symbol will always be equal to 1 for all prime. The Legendre symbol 1 over p is 1, because 1 is always a quadratic residue, right? Now, one more thing we can do is, if A is congruent to B mod P, if A is congruent to B mod P, then we can say that A over P Legendre symbol will be equal to B over P Legendre symbol, right? Because A is congruent to B mod P, so A over P means what? X square congruent to A mod P. If this has a solution, this value is 1, right? So that means there is some x such that x square is congruent to A mod P, but A mod P is congruent to B mod P. So if this has a solution, this will also have a solution, right? So both will be same. The Legendre symbol of x by A by P and B by P will be same if A and B are congruent, right? Okay, now we get back to combining Euler's formula or Euler's criterion to the Legendre symbol. So we know that A power P minus 1 by 2 is congruent to A by P mod P. This we have already established. This is coming from Euler's criteria. If P is an odd prime and A and B are integers relatively prime to P, then we can say that AB over P, the Legendre symbol, will be same as A over P times B over P. Why is that so? Because think of the number AB over P. We know that AB over P can be written as, according to this rule, it can be written as AB power P minus 1 by 2. But that can be split using the laws of exponents as A power P minus 1 by 2 times B power P minus 1 by 2. And now using this equation again, we can say that this is A over P and this is B over P mod P, right? So this is a very important result. From here, we can say that if this is 1 and this is 1, then AB over P is also 1, right? So if A by P is 1, which means A is a quadratic residue mod P, and B by P is 1, which means B is also a quadratic residue mod P, then the product AB by P is also going to be 1, which means AB will also be a quadratic residue. Similarly, if both of them are -1, -1, -1, which means A and B are both quadratic non-residues mod P, then AB will become a quadratic residue mod P, right? So we get these nice rules that because of AB over P equal to A over P and B over P, we can conclude that AB is a quadratic residue mod P if and only if both A and B are either quadratic residues or quadratic non-residues. So we have quadratic residues times quadratic residue gives quadratic residue. Non-residue times non-residue will also give a quadratic residue. But quadratic residue times non-residue will give a non-residue. Because then we'll have 1 and minus 1, so the answer will be minus 1. So remember these basic ideas. It comes from Euler's criteria plus the Legendre symbol, right? Okay. So now let's go to the next idea. So for which odd primes, P is minus 1 a quadratic residue mod P? We are trying to answer this question. For which odd primes is minus 1 going to be a quadratic residue? So if minus 1 is a quadratic residue, then the equation x square is congruent to minus 1 mod P should have an integer solution, right? This equation should have an integer solution. Now, basically what we are trying to find out is minus 1 over P. What is the value of this, right? Excuse me. So according to Euler's criteria, this should be minus 1 power P minus 1 by 2, right? This is the Euler's criteria. So this is equal to this. Now, we just have to answer when will this symbol become plus 1, right? This will happen when P minus 1 by 2 is even. So that means P minus 1 by 2 must be 2 times some K. That means P should be 4K plus 1, right? So if P is a prime which is congruent to 1 mod 4, then minus 1 is a quadratic residue mod P, right? Because if P is a prime of the form 4K plus 1, then we are getting that minus 1 over P Legendre symbol is equal to minus 1 power P minus 1 by 2, and P minus 1 by 2 is equal to an odd number because 4K plus 1 minus 1 is 4K by 2, so it is 2K. So P minus 1 by 2 is coming out to be an even number, my mistake. So it is becoming minus 1 power 2K, and that makes it plus 1, right? So we have found that if P is an odd prime, the conclusion is if P is an odd prime, then minus 1 is a quadratic residue mod P if and only if P is equal to 4K plus 1 or P is congruent to 1 mod 4. Okay. And now we come to the main idea of this discussion, which is the law of quadratic reciprocity. So how do we introduce that law? So think about two distinct primes. If P and Q are distinct odd primes, then there are two possible unrelated questions. So is P a quadratic residue mod Q? So suppose we ask this question, is P a quadratic residue mod Q? So we are trying to find out the Legendre symbol P over Q, right? P and Q are distinct odd primes, so obviously this fits the definition of the Legendre symbol. Remember, Legendre symbol was A over P, where A and P were relatively prime to each other, right? So this would be 1 if A is a quadratic residue and -1 if it is not a quadratic residue mod P. We are just saying instead of A we have P, instead of P we have Q. So is P a quadratic residue mod Q? And we can ask another question, is Q a quadratic residue mod P, right? Mod P, right? And this means that we are asking Q over P Legendre symbol, whether it is +1 or -1, and whether this is +1 or -1. There is no reason to suspect that the answer of the first question has anything to do with the second question. This could be +1 or -1. P and Q are two prime numbers which are odd, and they are relatively prime to each other, obviously. So P could be a residue or could be a non-residue mod Q. Similarly, Q could be a residue, could be a non-residue mod Q. On the surface, we should expect that there is no connection between these two ideas, right? However, it turns out that there is a beautiful relationship between them. So P over Q, Legendre symbol, and Q over P, Legendre symbol, they are connected. And that is basically the law of quadratic reciprocity. So I'll state the law now. So it says that if P and Q are distinct odd primes, then P over Q Legendre symbol times Q over P Legendre symbol is equal to -1 power P minus 1 by 2 times Q minus 1 by 2. Fairly simple statement. The product of these two Legendre symbols is equal to -1 power P minus 1 by 2 times Q minus 1 by 2, right? Now, obviously, if you think of the RHS is a power of -1. So it could be taking the value of +1 or -1, depending on the values of the exponent, right? Depends on whether the value of the exponent is a multiple of 2 or not, right? If the exponent is even, you get +1. If the exponent is odd, you get -1, right? Now, let's take the case of if the exponent is even. If the exponent here is even. So that means RHS will become +1, right? If the RHS is +1, that means P over Q, Legendre symbol multiplied by Q over P is +1. That means both P over Q and Q over P are 1 or both are -1, right? So basically, we can say that if both are +1, that means P is a quadratic residue mod Q if and only if Q is a quadratic residue mod P. If both are +1, basically both are residues of each other, right? P is a quadratic residue mod P and Q is a quadratic residue mod P, right? So the idea is both could be +1 or both could be -1. So both could also be non-residues right now, right? If on the other hand, we had RHS was coming out to be -1. If RHS is -1, what does that mean? That means P and Q product of these two Legendre symbols is equal to -1, which means one of them will be a residue and one of them will be a non-residue, right? So think about it. Let's analyze this exponent part a little bit. So any odd number will be of the form 4k plus 1 or 4k plus 3, right? And P and Q are odd numbers, they are prime numbers. So they will be of the form 4k plus 1 and 4k plus 3, right? Now, the exponent was p minus 1 by 2 and q minus 1 by 2, right? This was the exponent on the RHS. So we can show that if p is equal to 4k plus 1 and q can be anything, then obviously what will happen? P minus 1 by 2 would become 2k, which is even, right? So the product of an even and an odd or even number will always be even, right? So what we are saying that if any of the primes, any of the two primes, P and Q, are of the form 4k plus 1, then either P could be of the form 4k plus 1 or Q could be of the form 4k plus 1. If any of them is of the form 4k plus 1, then the product P minus 1 by 2 times Q minus 1 by 2 will be even, right? And we don't have to worry about other cases in that case. Any one of them being of the form 4k plus 1 ensures that the product is even. However, if the product has to be odd, then none of them should be 4k plus 1. That means both P and Q must be of the form 4k plus 3. If both are of the form 4k plus 3, then you will realize that P minus 1 by 2 is equal to 2k plus 1 and Q minus 1 by 2 is also some 2k dash plus 1. So they are both odd numbers now, and now the product is odd, right? So what is the conclusion on analyzing the exponents here? On the RHS, there is an exponent of P minus 1 by 2 and Q minus 1 by 2. If any of the two primes P and Q are of the form of 4k plus 1, then automatically the exponent is even, right? And if both the primes are of the form 4k plus 3, only then will the exponent be odd, right? So now, if the exponent is even or odd, we will know the power of minus 1 power even and minus 1 power odd. So the law of quadratic reciprocity can be rephrased in this manner. So first I'll write the original law that I wrote. So it is P by Q times Q by P Legendre symbol is equal to minus 1 power P minus 1 by 2 Q minus 1 by 2, right? This is the original law, and now we rephrase it like this. If P and Q are odd primes, both congruent to 3 mod 4, right? What happens if both are congruent to 3 mod 4? This part becomes odd. So that means the product on the RHS is minus 1. So that means P over Q and Q over P are equal to minus 1. So one of them is a residue and the other one is a non-residue, right? So we can say that they have different nature. They are residue and non-residue now, right? Then we say then P is a quadratic residue mod Q. P is a quadratic residue mod Q if and only if Q is not a quadratic residue mod P, and vice versa. So if P and Q are both odd primes congruent to 3 mod 4, then P is a quadratic residue mod Q if and only if Q is not a quadratic residue mod P, because the values of the Legendre symbols in this case must be opposite. If this is plus 1, then Q over P must be minus 1, right? And what is the second part of this? If either one of P or Q, if either one of P or and Q is congruent to 1 mod 4, right? Then we can say that P is a quadratic residue mod Q if and only if Q is a quadratic residue mod P. So in case any one of the primes is of the form 1 mod 4, then the product here will become 1. That means both of them have the same nature. They have to be both quadratic residues of each other or both quadratic non-residues, right? So now let's look at some particular problems and apply what we have learned so far, right? So first of all, let's try to find out what is the Legendre symbol of 3 over 101, right? So what is the usefulness of this symbol? So what is the question meaning here? This can be either +1 or -1 depending on whether 3 is a quadratic residue mod 111, right? Now that means we have to check this equation. Is it possible for some integer x to have x square is equal to congruent to 3 mod 111, right? Now notice that this will be quite involved, no? If we have to check whether there is some integer here, we have to check all the integers from 1 to 100 square, or technically at least till 50 square we'll have to check, right? So that will be annoying, mod 111, 101. So now we will use the law of quadratic reciprocity, right? Because we don't have to directly calculate this. We can calculate 101 over 3. Why? What does that mean? That means basically we are checking whether 101 is a quadratic residue mod 3, right? X square is congruent to 101 mod 3. We are doing the opposite Legendre symbol, right? Now this is obvious because 101 mod 3 is what actually? It is simple. It is simply 2 mod 3, right? 2 mod 3. So we can very easily check this, right? We can check this very easily because 3 is a small number. So we can say 0, 0 square, 1 square, 2 square. And these are the 3 possible residues. So you have 0, 1, and 1. So the answer for this is -1, right? 2 is not a quadratic residue mod 3. The only possible quadratic residue is 1, right? So 2 is not a quadratic residue mod 3. So 101 is not a quadratic residue mod 3. So the answer for this is -1, right? And now we apply the law of reciprocity. We say 101 over 3 and 3 over 101, right? Should be basically, technically we can write -1 power p minus 1 by 2. So 3 minus 1 by 2 times 101 minus 1 by 2, right? So from here we know that 3 minus 1 by 2 is 1 and 100, this is 50. So this is +1, right? This is +1 means the only way that can happen is if this is -1 and this is -1, right? So we already knew this was -1, so this must be -1. So we get the answer that 3 over 101 is -1. Think about it. We have applied the rules that we have learned in the previous 30 minutes, right? So I will just explain it again. We are checking whether 3 is a quadratic residue mod 101, right? Now, instead of checking that, we can check 101 is a quadratic residue mod 3. Now, that is pretty easy to guess because 101 mod 3 is 2 mod 3 and x square is 2 mod 3 is clearly not possible for integer x, right? So this value, this Legendre symbol is equal to -1. We know that, right? Now think of the alternative form of the law of quadratic reciprocity that we discussed just now. So think of the primes. 4k plus 3 is of the form of 4k plus 3 and 101 is of the form of 4k plus 1. If you think of the alternative form, we said that if any one of the primes p and q is of the form of 4k plus 1, then the RHS became +1, right? And that means both have to be of the same nature. Both p over q and q over p have to be either +1 or -1. And we already know that this is 101 over 3, Legendre symbol is -1. So that means 3 over 101 must also be -1, right? Let's do another example. Let's try to find out 97 over 101, right? So we are checking whether x square is congruent to 97 mod 101, right? Now, again, this will be a direct calculation of this will be annoying. So we'll try to do the opposite. Let's find out 101 over 97. So is there a solution to x square is congruent to 101 mod 97? And that is pretty simple because that is 101 mod 97 is 4 mod 97, right? So x square congruent to 4 mod 97, you can immediately say 2 is a valid integer solution, right? So that means 4 mod 97, 4 is a quadratic residue mod 97. So 101 is a quadratic residue mod 97. So therefore the answer for this Legendre symbol is +1, right? And if this symbol is +1, now we have to guess what should be the value of this, right? How do we guess that? Look at the primes. 97 is of the form 4k plus 1, and also 101 is of the form 4k plus 1. So we have seen from the alternative form of quadratic reciprocity that if any of the primes is of the form 4k plus 1, what happens is both the symbols will have the same nature. They will both be residues or both be non-residues. And we already know this is a residue, so therefore this must also be +1. So we have verified that there must be an integer such that this has a solution. The Legendre symbol 97 over 101 must be equal to +1, right? Now let's see an application of this law. So we can use the law of quadratic reciprocity. We can use the law to even find the quadratic character, to find the quadratic character, basically whether something is a residue or not, of non-primes modulo a prime. Non-primes modulo prime. So far the law was for two distinct primes, right? P and Q. So now what I will try to understand is what is 57 over 101, the Legendre symbol. But you notice that 57 is not a prime. However, we have learned the law AB over P, Legendre symbol was equal to A over P and B over P product, right? So we can say that this is 3 over 101 times 19 over 101, right? Great. Now we know from a previous calculation, we just did this example, 3 over 101 was 9 minus 1. We did this earlier just now. We got it by understanding 101 over 3 Legendre symbol, right? Now we check what is 19 over 101. 19 over 101 we want to find out. So easier way to find that out would be 101 over 19, which is basically x square is congruent to 101 mod 19, and that is basically 6 mod 19, right? Whether this has a solution or not, right? Now 6 mod 19, basically this is same as 6 over 19, and that is equal to 2 over 19 times 3 over 19. This is the product of two Legendre symbols, 2 over 19 and 3 over 19. Now let's find out what is 2 over 19, right? So 2 over 19 x square is congruent to 2 mod 19. So we can directly evaluate it. We can directly evaluate it by checking all the quadratic residues from 0 to 0 square, 1 square, 2 square till 9, 10, 10 square, right? That is one way. Or we can try to find 19 mod 2. X square is congruent to 19 mod 2, which is equal to 1 mod 2. And x square is congruent to 1 mod 2, that has a clear solution 1, right? So that means 19 over 2 has value 1, Legendre symbol, and 19. So now we have to figure out what is 2 over 19, right? So, right, the value of this should be -1, because 19 and 2 are both not of the form of 4k plus 1. However, we can just confirm it easily. We'll just do it like this, because right now I can't directly apply this because 2 is an even number. I cannot apply the law of reciprocity here. I'll have to actually check all the residues here, right? So it will be 0, 1, 4, 9, 16, then 25 will become 6, 36 will become minus 2, which is plus 17, then 49 will become 9, no, 11, and 64 will become 7, 81 will become 5, and 100 will become 5 again. So basically you can see I have checked the first 9 squares. After that the squares will keep repeating, and you can see that there is no 2 here. 2 is not a quadratic residue. So what we get is 2 over 19 is negative 1 here, right? And similarly 3 over 19. Notice that 3 is also not a quadratic residue, right? So 3 over 19 is also negative 1. So that means that 6 over 19 is positive 1, right? And if 6 over 19 is positive 1, that means 101 over 19, Legendre symbol is positive 1. Now think about what is 19 over 101. Notice that 19 is of the form 4k plus 3, but 101 is of the form 4k plus 1. So if any of the primes P and Q, one of them was of the form 4k plus 1, what did we conclude? That means that the RHS is even in that case, and therefore both the symbols P over Q and Q over P have to have the same sign. So if 1 over 101 over 19 is plus 1, then 19 over 101 is also plus 1. And now we have already found 3 over 101, which was minus 1. So the product of this is minus 1. So we have figured out that 57 over 101 is minus 1. Or basically, there is no solution to the equation x square is congruent to 57 mod 101. So notice that it takes 4 or 5 minutes of thinking and using the law of quadratic reciprocity properly. It's not a big deal, and we are able to solve questions that would otherwise be much more time taking and painstaking also, right? Finally, I'll conclude with two results, two supplementary results. You should check it out and see whether these work. So we are saying if P is an odd prime, if P is an odd prime, then minus 1, we have already seen this one. Minus 1 is a quadratic residue mod P if and only if P is congruent to 1 mod 4. And the second one is if P is an odd prime, then 2 is a quadratic residue mod P if and only if P is congruent to 1 or 7 mod 8. Notice this is an application of what we just now did. We were trying to find 2 over 19, right? Whether 2 is a quadratic residue mod 19. So if we knew this result, we would have said 2 is a quadratic residue if and only if P is 1 or 7 mod 8. So what is 19 mod 8? 19 mod 8 is basically 3 mod 8, and therefore it is not 1 or 7 mod 8. So therefore 2 over 19 should be negative 1, because 2 is not a quadratic residue. So remember this condition, it becomes handy sometimes, and this condition is clear, we had already discussed it. So that is a basic introduction to the law of quadratic reciprocity. Now, in the next video, we're going to spend some more time on it. We'll do some problems, and we'll also introduce the next part of the theory, which is the Jacobi symbol. So the Jacobi symbol is an extension of the Legendre symbol, and it is for not just for prime numbers. Instead of A over P, we will have A over N. So a slight generalization of the Legendre symbol. And we'll also do some problems involving quadratic reciprocity. So stay tuned for this. If you learned from the video, please like the video, subscribe to the channel. It's your support that helps me keep bringing these videos. So see you next time.